All right, so we got a goal. We've got a goal for our mitigation. We're going to set our carbon goals and sit down and see how we can do it. So again, one of the things that I mentioned is that this is a goal that's not arbitrary, right? It's not just some kind of random goal like we would probably want less carbon. When we look at all of the different aspects of climate, we talk about tipping points, right? And so again, there's lots of interrelated systems. Many of them have a point at which they can become critical. For example, like melting ice or something. At some point, we start to get this kind of runaway greenhouse effect, right? It's less albedo, more heat absorbed, and you can see we get back into those feedback loops. So many of these tipping points actually are kind of related to larger kind of big picture feedback loops. And what most scientists agree on is that if we look at, kind of 8 or 9 really big, like significant climate systems, most of those will get close to critical, or what we could call abrupt and irreversible climate change, the things that we might not be able to come back from in this range, right? But again, there's lots of little different kind of interconnected parts. And we're going to go through and look at a few of those tipping points and see how that kind of putting all of those together, that's where this number comes from. So again, it's not an arbitrary number. So one thing that can happen, as we start to see rising temperatures, and hopefully this will illustrate, how things get really messy really quickly, is we've talked about thermohaline circulation, right? The notion that these ocean currents are largely driven by kind of the sinking of dense water and the displacement of warmer water and then rising, bringing up nutrients, right? And that's tied to kind of marine biosphere and all of that. So if you remember, the driver for these thermohaline currents is thermo and haline. It's actually temperature and salinity. And so generally in the cold areas, what we start to see is as sea ice begins to form, partially mixed with fresh water, there can be a little bit of fresh water there. But as the ocean begins to freeze, salt water, as it gets cold, first of all, becomes more dense, but the water that's kind of sequestered into the ice actually also increases the salinity of the kind of leftover brine, if you were to think about it that way. And so it's cold and it's salty and it sinks. And as these, ice, as the sea ice, particularly in the Arctic, is kind of expanding and contracting, there's more ice and less ice over the course of 1 year. When there's more ice, there's essentially more water being pumped into the thermohaline system. When there's less ice, it slows down. And so you can kind of think about every year there's these pulses of water headed down through, even though it's active all year round. So one of the things that can be a detriment to that is actually melting ice from freshwater sources in continental areas like land ice, or here we're not talking about sea ice. But if we're kind of imagining ourselves, up by Iceland, Greenland area, that's where we're seeing the kind of initiation of these thermohaline downwelling currents. If there's a lot of melt coming from the continents, it turns out seawater itself is less dense than freshwater. And so when you have huge phases of melt, what happens is the fresh water actually will literally sit on top of the salt water. And that's a problem because now the fresh water is the water that's freezing and thawing, and it actually can't overcome this density boundary that's the kind of boundary between the saline water and the fresh water. And in a kind of weird turn of events, it essentially insulates the underlying seawater, meaning there's no ice being derived from it, and it's actually not getting colder. It's not losing heat to the atmosphere. And so that regulates the temperature of the seawater, and actually that shuts off this circulation. And we see, when we look at how quickly these currents, we see these currents are actually slowing down. So getting into the range of this level of warming, that's when we start to see increased melting in Greenland, which we're definitely seeing, right? There's more and more and more kind of dark land exposed every year. And that could potentially shut down thermohaline circulation, which is one of the biggest thermoregulatory kind of drivers on planet Earth. Well, when we think about, places like Antarctica, for example, there are huge sections of ice, in some cases, up to 4 kilometers thick, right? It's like 2.5 miles thick, of ice just kind of headed into the oceans. And one of the things that those ice shelves do is, among other things, is they actually slow down or impede the flow of ice into the oceans. They're kind of in the way, in a sense. And we've started to see massive break aparts of some of these kind of ice domains. So some of the largest ice sheets we have kind of both in Greenland and Antarctica are significant. And again, as those begin to disintegrate, you start to get this positive feedback loop. So now there's less albedo. That water, that kind of open ocean now is essentially black and is absorbing more heat, which can cause this positive feedback to melt more ice. But then more ice is coming sloughing off of the continents. So again, that's definitely observed and observable. That is very realistically happening. But again, we don't want that problem to increase, right? We don't want to see more of that. So the next kind of big picture tipping point, right? That's kind of what we're going through. We're looking at some of the major tipping points in Earth's climate system. Rainforest Dieback. And so the rainforest is a really interesting place. It's warm, and it gets an incredible amount of precipitation. And part of that, it has to do with nutrients in the soil. When we think about it, it's kind of a special problem, right? So when trees die in the rainforest, they tend to fall on the ground and they tend to decompose fairly quickly. And those nutrients are essentially used immediately. And there's enough rain that anything soluble that the plants didn't take up was actually washed out of the system. So, beyond, less than a foot, the soil is really nutrient poor. But that functioning foot of soil in the upper portion of the rainforest has a constant input of vegetation and a constant input of nutrients that can support that level of vegetation. So one of the things that happens is if you go in and you remove that vegetation to run cattle, for example, this is what's happening in the rainforest, now there's no more plants that are inputting nutrients into those soils, and those soils basically become sterile. Then we start to see land use change issues, right? So not only does the kind of sterilization of part of the Amazon rainforest by cutting things down, not allow trees to regrow, but also we've started to see droughts, right? So increased temperature and decreased rain, which is actually causing portions of the rainforest to actually die back. And again, that further reduces Earth's ability to consume CO2, and that CO2 then ends up pooled in the atmosphere. You remember our old friend, methane hydrate. So we talked about the methane gun and all of that, earlier in the class. Again, that's a great example of a tipping point, right? So we have methane hydrates, which is a very specific type of kind of 2 molecules intertwined, a methane molecule and some water. And it's in solid state, but it's really susceptible to temperature. And so if we see increasing temperature, we can see first of all, permafrost melting, which is one of the places that methane gets trapped. And again, potentially the release of methane hydrates in these shallow seafloors, generally in colder environments. But as that water warms, we're potentially releasing more methane. Again, going back to keeping this goal, right? So some of this we can deal with, but we're trying to prevent some of these tipping points. And another example of one of them. So coral reefs make up a really small percentage of the environment in the ocean, right? They're like, 0.5% of the ocean, maybe 1%. Don't have the number off the top of my head. But one of the things that I do know is that they support about a quarter of marine life. And one of the things that coral reefs are especially good at doing is playing a significant role in the carbon cycle, actually in the slow carbon cycle. So CO2 in water is consumed by all of this life and ultimately becomes limestone. But one of the things we've seen is with an increase in acidity, we've talked about ocean acidification, generally driven by rainwater picking up CO2 in the atmosphere, and that carbonic acid ending in the oceans. And so as the pH decreases or the acidity increases, same thing, these coral reefs have been experiencing bleaching effects. And so there's, the structure of the coral, but then the algae that live on them that make them, beautiful colors, this kind of symbiotic relationship. As those algae begin to die off, the corals essentially just become dead skeletons. They become white. We call that coral bleaching. We've had significant coral bleaching events in the past. And recently, it kind of happens every year. Sometimes they regenerate. Sometimes those are just dead corals. But again, that's essentially shutting off a big aspect of the carbon cycle, one of the major carbon sinks that we have. And this last one really has to do with changing some of these heat variables, right? And so we have this really intricate system of monsoons, right? Some portions of the world rely on these monsoons to be habitable. And as those monsoons patterns shift, the timing changes. We've seen kind of what we call like monsoon droughts over the last 30 years. And that is a really big deal because, again, it's not just like the wildebeests that are relying on the grasses in the plain, like we've seen in every National Geographic video when, the drought comes. But we can experience significant famine and displacement of peoples, right? So if we have, monsoons that are not sustained, as our global population is inching towards 8 billion, I think we'll be there fairly soon. You might actually be watching this video after that happened. But as we kind of are knocking on the door and surpassing 8 billion people on Earth, one of the big things that we're really concerned with is climate refugees, right? And so shifting monsoon patterns affects food production, can create famine, and can create significant problems kind of around that realm of climate refugees. Where the heck do those people go, right? Again, that's a recipe for disaster. So when we go back and we kind of cycle through, you can see here's a diagram that shows, how a lot of these tipping points are related. And again, it's a little bit sterilized and there's, lots of different versions of this diagram. Some things we included, some things we left off. But the notion that there's a handful, anywhere from 8 to 15 of these kind of climate tipping point areas, they're all interrelated. They all have kind of critical results with, even a limited degree of warming. They can each have kind of critical results, even with a limited degree of warming. One can affect the other. And if we think about, crossing over some of those tipping points, whether we cross all of them, whether we cross some of them, some of the things that can happen are, sea level rising, particularly when we talk about melting ice and generally heat. That displaces people, right? Many people live essentially at sea level. And if we were to melt all of Greenland, not saying that we are, but if we were, that's about 4 meters of sea level rise. That's 12 feet. That's a pretty big deal. Heat and kind of how we deal with that heat. So again, just in a kind of raw sense, right? So running air conditioning, consuming more energy, heat stroke, heat-related illnesses. Again, heat can also drive climate migration. It's just too hot in some place. You got to go somewhere more temperate. Food supply, so famine. If we're not able to produce enough food, usually kind of in a region or something like that, people are going to leave, right? And they're going to go and find food. And any of us would do that. And again, a lot of these are kind of, relating to the notion of people, right? People moving around. And that kind of brings us to this last issue, right? And this is what some climate scientists are really ultimately concerned about, is potential conflict that arises when you have displaced people. It's too darn hot. There's heat sickness. Kind of makes me think of, Dune universe. There's nothing for them to eat. And that's how wars are started, right? I mean, when there's people coming in, whether it's, for one reason or another, nobody's ever happy in that situation. And if we're thinking, these are our resources, we're not going to share these resources, that's when we could really start to see some fairly large global conflict. But again, we hope to not, right? We're just kind of outlining what might happen. This is, again, the reason why we have this mitigation goal of limiting warming to 1.5 to 2 degrees Celsius. So far we talked about adaptation to climate change, which doesn't really solve climate change. We've talked about mitigation, which hopefully solves climate change in the future, changing our behaviors, changing the way we generate energy. And then the next couple of segments, we're going to talk about how can we fix the problem, right? So here we're lessening the problem. The first aspect, we adjusted to the problem. Here we're trying to reduce the problem. And what are active solutions we can take to actually fix the problem? And that enters the realm of what we call geoengineering. All right, I'll check you in those videos.